Assalamu alaikum. I'm Sunela Hassan Kunjan, and I will begin our presentation by discussing the problem motivation literature review. Dataset and pre-processing steps of our project titled Predicting Myocardial Infraction, a data-driven diagnostic approach to early detection using machine learning. Cardiovascular diseases remain one of the leading causes of death worldwide, and myocardial infarction or heart attack is particularly dangerous due to its sudden onset. Many heart attacks occur without early warning, which makes early risk prediction extremely critical. Traditional clinical methods often fail to capture complex interactions between lifestyle, clinical, and behavioral factors. This motivated us to explore machine learning based prediction models. In our literature review, we analyzed multiple recent studies that applied machine learning to heart attack risk prediction. Existing works used models such as logistic regression, SVM, decision tree, methods, and clustering techniques. While many achieved reasonable accuracy, severe limitations were consistently observed, including small dataset, class imbalance, high computational cost, lack of external validation, and robustness check. These gaps inspired us to design a well validated and carefully pre-processed pipeline. For our study, we used the heart attack risk prediction dataset from Kaggle, which contains 9,651 patient records and 27 features. These features include demographic information, clinical measurements, and lifestyle, lifestyle indicators. The target variable is binary, indicating high risk or low risk of heart attack. Now, coming to data pre-processing, which was a crucial part of this project, we first ensured data consistency by checking data types and cleaning the target variable. The only categorical feature, gender, was label encoded. Fortunately, there were no missing values and no imputation was required. However, class distribution analysis revealed a significant imbalance between high risk and low risk cases. To address this, we later applied citizen-based synthetic oversampling, ensuring a balanced dataset without simply duplicate samples. We standardized all numerical features using standard scaling, which was essential for models sensitive to feature magnitudes such as HBMs and neural networks. Additionally, we performed exploratory clustering using k-means and applied PCA-based outlier detection, removing 731 samples to reduce noise and improve stability. With a clean, balanced, and well-structured dataset prepared, I will now hand over the presentation to Zubair, who will explain the modeling dataset and balancing the results.
I am Zubair Hussain and I will conclude our presentation by discussing the model implementation, dataset balancing, evaluation, and final results. After pre-processing, the dataset was split into train, test, and validation sets using a 70%, 15%, and 15% stratified split to maintain consistent class proportions. These ensured fair evaluation and data leakage of supervised machine learning models, including logistic regression, decision tree, random forest, AdaBoost, gradient boosting, supportive vector machine with RBF, kernel, and multiple MLP architectures. Overall, 9 models allowed us to compare linear, nonlinear, ensemble, and deep learning approaches. To address the earlier identified class imbalance, we applied CTGAN based oversampling. Okay, From here, we can see that before running Citigan, I installed Citigan by using pip install Citigan. Let me show you here. So after installing Citigan in the Colab notebook, for oversampling, we applied Citigan based synthetic data generation technique ensured the minority class samples were realistically generated rather than simply duplicated. Importantly, model performance remained consistent even after balancing, confirming that our models were learning genuine patterns instead of memorizing majority classes. So for evaluation, we used accuracy, precision, recall, F1 score, and confusion matrices. In medical prediction tasks, we emphasize high risk patients correctly is more critical than overall accuracy. So among all models, as we can see, the deep multiplier perceptron clearly outperformed others. It achieved a validation accuracy of 94.68% and a test accuracy of 94.14% approximately, with strong precision and recall for both risk classes. The close agreement between validation and test results indicates excellent generalization and minimal overfitting. So traditional models such as logistic regression and decision trees showed moderate performance, while ensemble methods offered incremental improvements. However, they do not match the deep learning model's ability to capture complex nonlinear relationships in healthcare data. In conclusion, our project demonstrates that machine learning, when combined with robust preprocessing, outlier handling, and dataset balancing, can be a reliable tool for early heart attack risk prediction. Future work will focus on external clinical validation, model explainability, and real world deployment in clinical decision support system. Thank you very much for hearing us.